Hey, what's up? All right. Specific heat capacity, calorimetry stuff. I think it's like 6.3, 6.4. Heat capacity, specific heat, calorimetry. Let's check it out. Check it out. I need to get a calculator out, don't I? Maybe a periodic table. Okay, guys. Let me share my screen. Okay, let's make this happen. Let's make this make sense, right? Okay, let's start. I'm going to start different. I'm going to start with specific heat, all right? Specific heat. Heat capacity. You might see something called molar heat capacity. You might see the word specific heat capacity, maybe, maybe not, all right? So I don't want that to throw you. Notice they're the same, except one says specific and one says molar, okay? So to me, that means this is, and I'll explain it further in detail, this is specific to the gram, to the or a gram of the substance, all right? And the molar heat capacity pertains to 1 mole of the substance. The substance can be anything, okay? Any pure substance. All right. Now, the specific heat capacity has a unit C, the symbol C. This is the symbol. It's also the symbol for the speed of light for specific heat capacity. And we are going to be using the specific heat equation and that is Q equals MC delta T. All right, you need to be very familiar with this equation. Q is going to be the heat. If it is negative, then heat was lost, therefore XO. If it was positive, then heat is gained, and therefore the process was endo. Recall that in every heat exchange scenario, the Q equals the negative Q. The gained equals the lost, right? That's an important concept here. This is the mass of the substance that gained or lost the heat. So if this is Q for A, this is the mass of A. And then here we have C, which is the specific heat of A. All right. And here, as you see, delta T is always change in temp. And it needs to be the final minus the initial, so that you get the correct positive or negative, which will allow you to get the correct positive or negative for your Q value. Because if heat was lost, then we should see this be a negative value, where our final temperature is lower than our initial temperature, and therefore when we solve for Q, it should be negative, right? So it's important that you do the final minus initial. It's important that you pay attention to that, all right? A lot of students don't. Now, let's look at some units here. C is typically in, oh my gosh, 4.184 joules per grams degrees Celsius. Joules per grams degrees Celsius. All right, so let's look at that, because what we need to make sure we actually understand is, what do we mean by specific heat, okay? So you need to understand, and understanding that just requires taking a minute to look at the units. So this is literally the heat joules, right? Joules is our unit of heat energy, okay? If you don't know that, Joules, unit of heat energy, all right? It's unit of energy. For us, it's heat, all right? So, and then grams is our mass, degrees Celsius. So the numerical value for for a substance's specific heat reflects the amount of heat required to raise the temp or lower, right? Either adding or removing. The amount of heat required to raise the temp of 1 gram, that's why it's called specific, it's specific to the gram, of a substance by 1 degrees Celsius. Okay? So, for example, water in its liquid state has a specific heat, right? The specific heat of water in its liquid state is 4.184 joules. So 4.184 joules of energy, maybe coming from the sun, is required to raise the temperature of 1 gram of water 1 degree Celsius. Okay? So that's what your specific heat tells you. How much heat is required to raise 1 gram 1 degree Celsius. For liquid water, this is your specific heat, okay? So if we wanted to raise it 2 degrees Celsius, we would need to add twice as much heat, okay? And then also with the amount of water, changes things. Okay, now that is specific. Notice up here, we said that we've got a molar heat capacity. Well, I could turn this 4.184 joules per gram degrees Celsius. I could make it molar, right? Because this is water. And I could say that there are 18.02 grams for every 1 mole. And then if I was to multiply that, 4.184 times 18.02, 75.40 joules per mole degrees Celsius. Okay, so that's how you could play with those units. I could go from specific to molar quite easily. Another thing that, okay, that takes me back here, because remember, we were looking at our equation and we were looking at our units. So we just said that, right, C is joules per gram degrees Celsius. Your mass, therefore, must be in grams. So if you're not given grams, you need to make sure you have grams. And when you solve for Q, it will be in joules. Okay? Often, when we have a molar heat capacity here, it is in kilojoules. And then it almost turns into our enthalpy. Okay? We take the joules per gram and change it to kilojoules per mole. And we now have the units for enthalpy, all right? I think I did that right. All right, but typically with enthalpy, that temperature isn't there. So we'll get more into that, but I want you to just see how simple it is to manipulate those units there, all right? Another thing that we need to talk about is notice that you've got a change in temp here, all right? You've got a change in temp. Well, it just so happens that Kelvin, right, and Celsius are the same scale. It's just that 0 starts at a different value, all right? And Kelvin's the lowest is 0, and Celsius, the lowest is negative 273. So the scale, it's the same scale, it just starts at a different place. Therefore, the change in temp degrees Celsius is equal to the change in temp on the Kelvin scale. Just take it, right? If we change 75 degrees Celsius minus 25 degrees Celsius, the change in temp equals 50 degrees Celsius. If I was to take both of these numbers and add 273 to them, I now have 348 kelvins. This is 298 kelvins. If I subtract them, the change in temp equals 50 kelvins. So the temperatures, the change in temp is the same. The temperatures aren't the same, but the change in temps when they change are the same. That would not be the case on the Fahrenheit scale. Okay, there we go. Now, simple equation. And what we need to do is talk about how it gets applied. It gets applied by using a calorimeter, okay? Gets applied by using a calorimeter. And this calorimeter, actually, I'm going to make it more like this. It's a cup, all right? Imagine you've got a styrofoam coffee cup here. And what we're going to do is we're going to put some water into this styrofoam coffee cup. And we're going to measure the exact amount of water that we put in there. And we will very likely utilize the fact that 1 gram of water, or rather, it would be more utilized in this sense, that 1 milliliter of H2O is equal to 1 gram of H2O, right? Because the density of water is most close to 1.00 grams per milliliter, all right? So oftentimes you're given a volume, and we either make the assumption if we're in the lab, or the problem gives it to you, the density, and we go from volume to mass. I need to know the exact amount of water that I put into this coffee cup, which we are going to call a coffee cup calorimeter. Calorimeter, all right? In this coffee cup calorimeter, I will place a thermometer. I will place a thermometer, all right? I like to say thermometer. I will put a thermometer in here. I'm going to measure the the change in temperature, right? That's my thermometer. Okay. And then in this water, I need to have a system. So what you need to really, really realize is the water is the surroundings, right? Water is the surroundings. What could my system be? It could be so many different things. It could be me taking some hydrochloric acid and putting it in there and diluting it. And that would cause some heat exchange. And I could measure the heat exchange of that solution, of that process. And I could relate it to the amount of particles are there and go from, joules to grams to kilojoules to moles, right? Or maybe I'm going to get a salt and I'm going to dissolve it in there. And I'm going to measure the change in temperature. And I'm going to relate it to the amount of water and the amount of salt and start calculating some heat exchange values or some specific heat values or some enthalpy of solution values, okay? So what it's important to realize is when you utilize this thermometer right here and you get the change in temperature of that water solution, whatever it might be, you are measuring the temperature change of the surroundings, okay? And we will solve for Q of the surroundings. This is most important, is equal to negative Q of the system. So we cannot measure the system, but we can measure the surroundings. And then we can apply what happened to the surroundings to the system because of this right here. Boom. Let us go. One more thing. Nah, let's just go. Let's start applying this, okay? This is a good level specific heat problem. Kids in my class last year, you did this last year, all right? I'll push y'all. All right, let's figure out what's going on. 73.5 grams of aluminum is heated in boiling water to a temperature of 98.7 degrees Celsius. So if the water is 98.7 degrees Celsius and the aluminum is in the water at 98.7 degrees Celsius, we would imagine we've got a thermal equilibrium situation. So we would say that the initial temperature, of the aluminum would be the 98.7 degrees Celsius. Okay. The aluminum is then placed in a calorimeter containing 1,500 grams of water. That's important. Notice the extra sig fig they gave us. At a temperature, so the temperature initial of the water is equal to 25.40 degrees Celsius. The temperature of the water in the calorimeter upon the addition of the aluminum, okay, increases to a final temperature of 28.20. What is the specific heat of the aluminum? Okay. Last thing I need to realize is I have another thermal equilibrium situation. Right now, the aluminum is sitting in the water, and the water's final temperature with the aluminum in it has reached 2820 degrees Celsius. So therefore, the final temperature over here is also 2820 degrees Celsius because the two are at thermal equilibrium. Just as these two were at thermal equilibrium in the beginning, okay? All right, so what I'm going to do here, and I wish I had a little bit more room, is I know that the specific heat of water, it would probably have been provided to you, is 4.184 joules per gram degrees Celsius. I'm going to, what you're going to do is write Q equals MC delta T. All right, sorry. I was going to see if I could possibly, this thing stinks sometimes, y'all. There we go. Never mind. I just want to make it like go down. Okay, we won't do that. Let's stop doing whatever I'm doing. All right, let's go like this. Let's go Q equals MC delta T for the water, right? Q H2O equals M H2O C H2O delta T H2O. All right, so the heat gained by the water is equal to the 1,500 grams of the water, the specific heat of the water, and the change in temperature of the water, which if I look up, it went from 28.2 to 25.40. All right, so let's everybody calculate that real quick. So typically in a free response problem, this would be like letter A, right? How much heat was absorbed by the water? You would want to make sure that you had proper sig figs in a problem like this. This could easily be a sig fig problem. They don't always measure your sig figs, but they often do, or grade on sig figs. 1.757 times 10 to the fourth, right? Notice here that in our units, grams are gone, our temperatures are gone. With that, we're left with joules. We're solving for energy. That is good. Okay, now imagine it's a free response. How much energy was gained by the water, or how much energy was lost by the metal? Well, QH2O equals negative Q aluminum, right? So the heat, this was lost, no, this was gained by the water, right? So QAL is the negative of that. The heat, the aluminum must have lost 1.57 times 10 to the fourth joules because the water gained 1.757 times 10 to the fourth joules. Okay, so I figured out how much heat was gained by the water by using my specific heat equation. I said that equal to an opposite the amount of heat that must have been lost by the metal. Now I can go Q aluminum equals mass aluminum, specific heat aluminum, change in temp aluminum. All right, and I'm going to do that right here. Let's see, I'm looking up, the aluminum was 73.5 grams. So I'm just going to read past that stuff. I apologize. Those are my other practice problems. I'm solving for the specific heat of aluminum. I knew it was equal to the heat lost by aluminum, which was negative 1.757 to the negative, to the fourth joules. And the change in temperature of the aluminum, let's see, it was finally at 28.20. It was initially at 98.7, so it's minus. Notice that will give me my negative value, which with this other negative value will give me my positive value for C, which is a requirement. So I'm going to pull those over here. Let's see, on negative 1.757 second E4 divided by parentheses 73.5 times parentheses 28.2 minus 28.7 parentheses equals. All right, it looks like we have a specific heat of 3.391 joules per gram degrees Celsius. Right? So that's the specific heat of aluminum. If you look at the specific heat of water, it is 4.184 joules per gram degrees Celsius. So the last thing I want to point out, and I'm sorry for these extra practice problems in here, is that even though aluminum lost 1,700 joules of energy, and water gained 1,700 joules of energy, right? Even though the heat exchange was equal, right? Because that's the law of conservation of energy. The temperature change is not equal, right? The temperature change is dependent upon specific heat values, right? The lower the specific heat value, the easier the substance heats up, right? It takes aluminum 3.391 joules to raise 1 gram, 1 degree Celsius. However, it takes water 4.184 joules to raise 1 gram, 1 degree Celsius. Therefore, when I add the same amount of energy to both of these, I'm going to have a greater change in temp here due to the lower specific heat value. All right, and I think that can kind of end this for now. All right, peace out.